Hello and welcome to All Space Considered online, everybody. This month, we are pre-recording All Space Considered, and this is the online-only version. We have an in-person event on the third Thursday as we normally do. This show's being loaded on Friday, however. We're premiering this Friday at 8 p.m. But our in-person guest did not want to have the lecture streamed, so we decided to put together a show just for you. So we normally have it on the third Thursday, and normally it would be March 20th, but this is premiering the 21st. We wanted to keep the date the same because some of you got confused when we were moving the date and the day around. We want people to come in person to see the show, so it's on the third Thursday. Come on in and see it. If it doesn't show up online, well, it might be one of those shows that got an embargo that we couldn't bring you. But today, in front of an empty theater, I don't know if anybody can see the empty theater there. Hello.
What's up, nobody?
Nobody. We have a couple of folks
How's nobody
here to
doing?
help us. But we are here for you, and we hope you enjoy tonight's show. We've got a lot of really great stuff. All Space Considered is brought to you by Griffith Observatory, the City of Los Angeles Department of Recreation and Parks. And as always, we like to thank Griffith Observatory Foundation for all the support we get for so many of our programs. Tonight, well, of course, I'm Dr. David Reitzel, and with me is Laura May Abram, Bill Cronenberg, I don't know, you're making me laugh, Bill, Ginger Rose Brooker, and Jared Head. Now, Ginger, you're brand new to the show tonight. You do astrophotography, so welcome, and we're going to start showing off some of the beautiful astrophotography images that we get here.
Thank you. Thanks so much for the introduction. Yeah. Happy to be here.
There was an announcement made about one of the nearest stars to us, the fourth nearest star, called Barnard star. It's a red dwarf. It actually is the fastest moving star apparently in the sky. It's called the proper motion of how it actually appears to go through the sky. It's moving really fast. So, year to year, you can actually map out the star's motion if you take pretty accurate photography. People have been doing this a long time. So it's been of interest to people a long time. They thought, could it have planets? Well, it was learned that there was one exoplanet around it, and now we've learned about 3 more, which is really pretty darn cool. This movie here, we follow along one of those exoplanets, a little small rocky world that orbits fairly close to its star. Again, the star is fainter, cooler, less massive than our sun, which means these planets, although they're pretty close, they orbit in a matter of days. They're probably baked by those UV blasts that come off it, the flares that come off of red dwarfs. So I doubt you're going to get any sort of habitability, but you can see what this looks like. But we're starting to see it more and more common of systems of planets or exoplanets around other stars rather than single planets going around them, which is kind of what we thought. We've got 8 in our own with lots of dwarf planets, lots of minor planets, lots of other stuff in our solar system. In fact, that's our second story. Bill, yes. You pointed out this month there were some interesting things going on with some icy moons.
Icy moons.
You want to grab a remote there, you can do it. The icy moons of our solar system, some of these are bigger than our moon, first of all. Ganymede, Callisto, they are bigger than our moon. And they'd probably be planets on their own right if they didn't orbit something much bigger.
That's true.
But what is the news about these icy moons? What's going on?
Well, there are 3 altogether that have something going on that we want to report on. I'm sure there's stuff going on all of them in some way or other.
Yeah.
Europa, Enceladus, and Callisto. Europa and Callisto are both moons of Jupiter, and they're both Galilean moons, meaning they were actually discovered by Galileo himself back in 1610, and Enceladus orbits Saturn. So here we go. This is what we want to find. All of these moons have some sort of icy exterior. That's why we call them icy moons. And a lot of that ice is water. In fact, Europa, way back in the 1960s, they determined that the ice was largely, if not all, water ice. And they did that with ground-based telescopes doing spectroscopy on the reflected light. So that's what they know. But this is what happens on Earth. You have a big icy exterior, but then you have liquid water underneath it. So that's what we want to know. Is there liquid water?
Why do we want liquid water?
Well, I was going to get to that a little later, but life, of course.
Okay.
You need it for life. So if we want to find life somewhere else, and we really do.
I just thought you were thirsty.
Yes, and I like a little ice in my drink. Okay, so now here's the thing. The Jupiter itself is like 5 times as far from the sun as Earth. So it's cold out there. How could there be liquid water for which you need heat? Well, this is how. This is sort of an animation of what a moon like Europa might do as it travels around Jupiter. As it gets really close, it gets contracted by the intense gravitational field of Jupiter, and as it gets farther out, the gravitational force drops off exponentially, so you have less and less gravity, and then it can relax a little. So the squeezing and releasing creates something we all understand, friction. You rub your hands together really fast, you create friction, and you can feel the heat. Heat also happens here, and we think that is why some of the ice might
Is silly
stay.
putty still a thing? 'Cause I think if you take silly putty and squish it back and forth, back and forth, back and forth, it warms up. It gets hot.
Oh, that's right. Yeah.
Yeah.
Well, it's the same principle
Yeah.
as works in an
Totally
icy moon. Now, so that's how it could happen. Now, why do we think there might be an ocean underneath? Here's one thing. If you look at the moon, which has been around for several billion years, you see lots of craters because over that time, lots and lots of things impact the moon. Europa's been around that long too, and it has a whole different kind of structure on its surface. You see some craters, but not a lot. If the ice is floating on a liquid underneath, it's going to grind and stuff and move and erase features like craters. And also, it looks kind of a lot like Earth's sea ice. So the same sort of fractures and lines and things that we have on our ice that floats on water are found on Europa as well. This is exactly what we're looking for. Now, this is the hydrothermal vents at the bottom of our ocean on Earth. And this is, you wouldn't be able to see this. This is pitch black down there. It's so deep. But they turned on lights to take this video. And you see chemistry coming out. You see heat coming out. You see life down there. A lot of scientists now think that life on Earth might have started down at these hydrothermal vents and evolved its way up to the surface. This I just added because it's kind of fun. This is the path of Europa Clipper to get to Europa. And it was launched and it went to Mars and it looped around Mars. I was looking at Mars every night around then just to see if I could, of course, couldn't see it. And now it's headed back to Earth. Now that seems totally counterintuitive.
Now this is a mission that's going to go study Europa out at Jupiter.
That's right.
So
It's ultimately heading to Jupiter. Thank you for pointing that out. That's exactly where it's going. But right now it's coming right back at us. Why is that? Well, it's because it's going to do it did a gravity assist acceleration around Mars, and now it's going to do another bigger one around Earth because Earth's mass is even bigger than Mars's. And then it should have enough speed to get to Jupiter and Europa by, let me see if I can read that. Yeah, it's going to be in 2030. April of 2030. April 11th, 2030. Mark your calendars.
In fact, we had a guest talking about that. If people want to go watch the old episode, Dr. Papalardo.
That's right.
Oh, right.
The
Good
PI
point.
on the Europa Clipper came to talk about this. So
Good
one of our
point.
previous episodes.
There you go. All right. So here's an artist animation of what it's going to look like. The mission is actually, two things. One, it's not a life-seeking mission. It's not trying to find little green man or even single-celled creatures. What it's looking for is habitability, evidence of conditions underneath the ice that could be habitable. And it's not orbiting Europa, it's actually orbiting Jupiter and doing flybys of Europa. And it's going to do 49 of those altogether. And they're going to tweak the direction just a little bit every time so that it covers the entire moon. Goes all the way around in 49 flybys. I don't have time to go into what it's going to look for, but I got to tell you that the primary mission, like I said, is looking for habitability, not life. But there are all sorts of instruments, and let's see, where are they? Wait, why isn't it going forward? There it is, okay. All sorts of instruments. If you're interested in going into the weeds on this, just go to nasa.gov and in the little search box type in Europa Clipper, and you'll find out so much. But it's going to check for, it's really going to no slam dunk one way or the other whether there is like a salty ocean underneath the surface, how thick the surface ice is, and so on, maybe where the thinnest parts are, in case eventually we decide to try to cut a hole through that and, I don't know, send a camera and a light down there and try to find fish or something. I hope that happens in my lifetime.
Fish sickles.
Fish sickles, that's right.
Europa
No,
sushi.
but actually not sickles because the water in there, I understand, could be heated to as
warm. That's right.
200 degrees
Right.
Fahrenheit,
No fish
possibly.
sickles.
It's hot. It's very hot water, actually. Hope it's not too hot for life. Anyway, I encourage you to go look at this. So now we have Callisto. Callisto is another moon of Jupiter, another Galilean. And it was studied by the Galileo mission several years ago. And they did a search for a liquid water ocean underneath and found it. And the way they do that is this moon travels through Jupiter's really powerful magnetic field. That magnetic field induces a current. If you have a liquid water ocean with some salt in it, it will induce a current underneath that ice, and then that current will actually induce another gravitational field. A lot weaker, but still you could see it. And they found it. However, this moon also has a very powerful ionosphere. We have an ionosphere on Earth too. It's the highest part of our atmosphere. It's full of charged particles, protons, and electrons. And because of that, they thought that that's a very conductive environment. And what they find, electromagnetically, they thought, well, that actually could be coming from the ionosphere, and therefore, all bets are off. We don't know if this thing has liquid water ocean underneath. But then some people just recently came along. They took the data and they extracted what the ionosphere should be capable of, and what was left does indicate that there could be an ocean under there. So that's that. Yes.
I was going to say, that's such a cool thing because you've got this old data, and a lot of people will often be like, why are you collecting this kind of data? Like, what are you going to do with it eventually? And it just shows that even like 30 years in the future, we can look back on that old data and be able to figure out new things that we didn't even know beforehand.
We found exoplanets from some of the old glass plates from 100 years ago, looking at the atmosphere of polluted white dwarfs. And old data is good data, frankly.
Yeah, that's true.
Well,
bad data. Well, I guess there's bad data once in a while.
Don't mind me, folks. I'm just over here having an allergy attack as people are talking about icy moons. A friend of mine does that work with the polluted white dwarf, Jay Farihi. He's still
it was
University
actually
College
him who
London.
found it.
Yeah, he's cool, cool dude. Know him well.
Now, one last thing is this is sort of a diagram of what they think was going on with Enceladus, the hot water shooting water and salts and stuff up through between the cracks as geysers. And this is an actual video from the Cassini mission as it flew by Enceladus, which has an icy exterior, of course. And you can see little tiny changes in that geyser, which indicates that something, I mean, if it's liquid coming out, well, of course, it turns into ice crystals immediately, but it changes. It's a geyser. So the thing is, somebody recently did a study, looked back at that data, trying to understand how it worked, and they decided that it really could come from not the interior of Enceladus, but from the actual exterior, where the ice itself, especially if there's salts in there. They throw salt on the road to keep it from freezing. It lowers the freezing point, and you get mushy, salty goo instead of ice. And that's what they think this could also be, and it could be propelled into space by the heat created again by friction of basically moving ice sheets. So that could explain these, but it still doesn't say that there's no. It's not. Right. They didn't come up with there's no ocean inside Enceladus.
Yeah. Well, and on top of it, this is them saying you can make these jets, or you might be able to if these conditions are like that. Yeah. We still don't know for sure. So they're saying there's a variety of ways to do it.
Right.
Sometimes that confuses the public. They'll hear one thing and then another thing and another thing, and what it is oftentimes is folks saying these are various pathways that the same thing could happen. And then we need to go do further investigation to narrow it down, and maybe sometimes it might be a combination. Maybe there's one that goes all the way to the ocean, and then smaller cracks.
That's true.
We just don't know.
Yeah. So the last thing I want to say is this picture you see is from the Cassini mission from several years ago, which we loved here. We reported on Cassini all the time. And it did fly-throughs of these geysers, and it determined that, first of all, there is a lot of water ice in them, and secondly, that the building blocks of amino acids are in there chemically, and amino acids are the building blocks of proteins, so it's very life interesting as well.
And there's some new moons too. I believe we've upped the number of moons of Saturn to 274.
Yeah, it's just
there's always candidates, but they've just done a kind of big data sweep and confirmed a whole bunch.
Just when you think you've got it all figured out.
I know.
Just come in and throw in double the moons.
There's so many moons to discover, even in the solar system still. But I suppose we could call them moonlets, though.
Well,
Are they
Yeah,
itty
yeah,
bitties?
that's
they're
true, they're
small. They're orbiting in a more chaotic
them,
fashion, but still they are little
They're
moonless.
moons.
Has anybody, IAU or anybody, come up with like minimum diameter for something to be a moon and not a moonlet?
Bill, you're just here to cause trouble, aren't you?
Yeah.
I am.
Just here to cause
This is
trouble.
going to be the Pluto's
Anyway,
a planet
that's-
debate for moonies.
Gosh, imagine if we
luminous.
reclassified the moon. People would be angry.
Oh yeah. No.
And speaking of moons, we just had a lunar eclipse, and it was really spectacular. It was visible throughout, well, most of the nation got to see it. Half of the world gets to see it, a lunar eclipse when they happen. Ginger Rose, why don't you tell us a little bit about the lunar eclipse?
Yeah, so here in Los Angeles, it was quite a spectacular event. We got a lot of great images. This first image here is actually taken by Laura May. Do you want to talk about the equipment
Yeah,
you
so
used?
this was actually an older image. You might have seen it on our social media. This was an image from May 2022. And so we also had an eclipse that was visible through most of the Americas. So this is a view of it that I shot from a little hill just to have the eclipse over Los Angeles and over Griffith Observatory.
It's a beautiful shot. You got the observatory in the background there.
Now, of course, eclipses start with a partial phase. Do you know who took this one and how we got this shot?
Yeah, this image is from one of our museum guides, Jonathan Conrad. He was using a telescope, and he just took this with an iPhone, which is pretty incredible. You can see that first phase there. And then going to the next photo, you see the full, this I believe is also, this one actually is from David Pinsky, one of our museum guides, and this is through his refractor telescope. So this is a little bit, you'll see the definition is a lot better in that picture as well.
Here's a shot of totality that we got from Griffith Observatory itself. So this, I think I took a picture of our screen, believe it or not, is my memory. So I cheated a little bit. That bright color, the almost bluish color that's at the top, is the moon was going through, not dead center of the Earth's umbra, but a little bit up higher. And the very edge of our shadow actually has a little bit of blue light going through it. It's from the ozone layer of our atmosphere that actually absorbs red light. So some of that red light that normally is refracted and sent into the moon, well, the blue light made it there instead, and it was high enough.
And we don't see it on every eclipse. There's actually a scale, the d'Anjou scale, of the kind of colors you'll get on lunar eclipses. And so only some of them, I've been trying to shoot that little bit of blue for a couple of years again, and it's been a while since I've seen it, so.
I know I was telling people, like, it's going to be different every time, but you're actually seeing every sunrise and sunset reflecting on the moon.
Pretty amazing.
So it's so impressive.
Yeah. Now, when there's a lunar eclipse, something else happens, and you've got something cool to show us here. What
Yes.
what are we seeing here?
So this is from the Blue Ghost mission that is on the moon, and you can actually see, you're looking at the sun in this image. And this is pretty impressive because they just landed this March 2nd, I believe.
Yeah. Yeah, just March 2nd, and
Perfect
they
timing.
took a picture.
Yeah, perfect timing. And here is a solar eclipse from the moon. How
Yeah.
impressive. How cool is that?
Yeah, so the way the alignment works is you have the Earth, the moon, in between the Earth and the sun. Oh, sorry, that's when there's a solar eclipse as viewed from Earth. So what's happening here is you've got the moon, the Earth, and then the sun. So if you're on the moon looking towards the sun, the Earth is blocking it. So that's actually, that's 4 times bigger in the sky than a solar eclipse would be for us. Because Earth is 4 times bigger than the moon. Anyway.
Maybe one day we'll travel. Maybe one day we'll travel to the moon and actually see our lunar eclipses as solar eclipses.
Would we call it like a Terran eclipse, like a Terra eclipse, or
I
would
think
solar
so.
eclipse still apply
Yeah.
pretty well?
I think it's still solar, but I don't know. It's a great question.
Yeah, Terra eclipse. I like it. I think we should coin it.
Now,
I like this shot because
Copyright
of the
it,
diamond. It's the diamond ring.
diamond
shot,
ring effect,
that
exactly.
we get here from. We got a bunch of great pictures from the eclipse, the April 8th eclipse.
Yeah. There were some good ones. Now, at Griffith Observatory, we like to celebrate the eclipse, like many cultures do, by assuming a beast of some sort, a monster, or a dragon in this case, has eaten the moon. And in fact, we might have a dragon here to tell us a little bit about it. The dragon shows up and eats the moon, and then we have to chase that dragon away. But the dragon's returned briefly to say hello to everybody.
It's a very friendly looking
Ella Ritz,
dragon.
everybody. Ella Ritz, our video production coordinator here at Griffith Observatory. You joined us during the eclipse, and you put on a dragon costume. And if Ginger shares her microphone with you,
Yes.
what was that like?
It's always a very riveting experience. Everyone knows that I'm among the most intimidating of coworkers around here, so bringing on some ferocity is no surprise.
Yeah.
But you're very committed. I remember we were readjusting your tail at one point right before, and
Yes.
secret Targaryens.
Yeah. Now, the way this actually works is our director, Dr. Krupp, gets on the microphone and lets people know that a dragon, a beast, has eaten the moon and we need to drive it away, and he starts leading chants of "Dragon be gone." So, as you see, we were successful once again at driving the dragon away. And Ella's sneaking off to the side there again. She'll return for the next eclipse. Actually, she's one of our staff that makes All Space Considered possible, everybody. So thank you, Ella. Thank you so much. But it's a lot of fun to do that. But people get together for lunar eclipses. In fact, Ginger Rose, you were saying there was a whole star party that was happening.
That's right, yes. So the Los Angeles Astronomical Society, they hold star parties every Thursday down at the Sunset Triangle in Silver Lake. And I was able to make it out to this, and it was truly incredible to see the crowds that were there. I mean, there were a lot of people. They had a bunch of telescopes set up, ready to view the eclipse. And I thought it was really cool. There was a moment where everyone is just looking up at the moon and they're all howling. And the energy was
Started
just
to howl.
amazing. It was so much fun. Yeah.
Eclipses
Yeah.
always bring that out of people.
I
They
think,
kinda
we
go
even have
feral.
I think we have a little clip of that howling to show.
We do,
can
yeah. There
bring
is
that
a
on.
video that we can show about that.
Well, that is a lot of fun. In fact, every year I go out to the Burning Man Festival and people howl at the sun when it sets. Because there's been a hot day, you're baking in the sun, you're out in the desert, that sun goes down, the relief is there, it's going to cool, well, usually it cools down. So it's a kind of a human thing to do. I don't know, you're howling like a wolf, but it brings people together. And eclipses really do bring people
I think we
together.
should start
It's a lot of fun.
meowing.
Yeah.
Meowing at sunset.
I'm more about cats. so,
Yeah,
That's fine.
Well, I actually some of us do that out there. We because it's funny.
Well,
There you
that-
go.
As
and
everybody's going, what was
I
that?
was saying, I always learn something new, too, with my equipment and my setup. I mean, I was battling some clouds, and I had to readjust the tripod a bit, but I got some cool pictures from it,
Yeah.
so,
Well, fantastic. Hey, if any of you got great photos of the eclipse of your own astrophotography, go ahead and send it in to us. We're on social media. You can find us and send them on in, and maybe we'll feature you. Well, we have a couple of very fun features to do tonight. It is Women's History Month, and we've decided to focus in on women in space and then also women at Griffith Observatory in honor of Griffith Observatory's 90th anniversary. But we're going to start off with a wonderful presentation that you've put together about women in space, Lorme. So if
Yeah, and I put
take it
this
over.
together with Haley Bricker, who was supposed to potentially chime in, but I'll be presenting this today. So, the history of women in space, obviously interesting and riddled with all sorts of challenges. And you might be wondering when the first women went to space. Well, it was in science fiction, of course. And we have here, this is to show you a book that was originally called Les Exilés de la Terre. In English, it was translated as The Conquest of the Moon. It came out in 1889. It was written by a French author, André Laurie, who actually worked with Jules Verne, very, very famous sci-fi author. And the story revolves around this group of scientists, engineers, and entrepreneurs who think that instead of figuring out a way to travel to the moon, it would make more sense to bring the moon down to Earth. There are some, there's some physics problems here. But there is a character, the lovely Mrs. Gertrude Cursain. She's the beloved of the hero. And when the men decide to explore the lunar landscape, she protests at being left behind. And she says, "I'm quite tired of being a useless member of society, and I demand my share of work with the rest." And I think that actually is quite representative of a lot of women who early on in aviation were involved in aviation and wanted to be part of also, the budding space race. And so in the book, it's actually quite neat because she takes part in astronomical observations and on her own, and she's instrumental in discovering the remnants of an ancient lunar civilization, and she explores the entire surface of the moon on her own. So a pretty neat story if you can find a copy of that. And of course, in more recent times, we have a lot of fictional astronauts. We were debating, in fact, which ones to include. You know, do some people in certain, for example, in Alien, do they classify as astronauts? Ripley and those characters, but of course, many people. You know, unclear, right?
Unclear.
But of course, one of the most famous characters is, of course, Sandra Bullock's character in Gravity. This whole film kind of, you know, centers on her experience of space. And so, where does the inspiration for this come from? There were many, many pioneers to these characters. So this is an image from 1915. Well, so in 1959, this is an image of Betty Skelton. And she became the first woman to undergo the physical and psychological tests of NASA's Mercury 7 astronauts. And, you know, this opened the door for many opportunities for women. She actually had quite an impressive resume. At 18, she received her commercial pilot license. She was certified as a flight instructor the following year. And she went on to set 17 aviation and automobile records. So quite impressive. In fact, there are some trophies named after her in aviation and aerobatics, do we call them? Aviation aerobatics, you know, when they do all these tricks in planes.
Yeah, aerobatics.
And however, what's interesting is that this picture was taken as part of a story for Look magazine. And the tests were basically administered at the request of this magazine for an article, right? So she wasn't part of these kind of official tests. It was done for this article. But she was very close to many of the astronauts. They nicknamed her 7.5, and she was even awarded. Yeah, so here's the cover with the rather interesting, you know, little title: "Should a Girl Be First in Space?"
Did they call the guys boys?
Yeah.
You know, that's a good
good
question.
point,
Yeah.
It's a good question. But yeah, so that was the February 2nd, 1960 cover of Look, and so, but you know, she never ended up going. She was given honorary wings by the Navy, but nothing changed. And she is quoted as saying, "I complained that NASA wasn't giving more thought to women pilots, and she really wanted to fly in the Navy, but you know, all they would do is laugh when she asked." So we have to think about how far we've come in just about 60 or so years. That, you know, a headline like this, I think, is not necessarily what we would have today. Now, this is Geraldine Jerry Cobb. She was one of the very first women to attempt to become a NASA astronaut, and she was the first of 13 female candidates to successfully pass all 3 phases of this Mercury test program. So she sought testing as early as mid-1959, and she began recruiting other female pilots to undergo testing in 1960. And now all these women, again, they sought these tests themselves under the belief that passing the test would actually allow them to become astronaut trainees, right? And there was someone who was very important in helping for this mission was Dr. Randolph Lovelace. He was a NASA scientist, and he conducted the official Mercury program tests for the men. And he was also the one who administered the tests for the women at his own private health clinic without the permission of NASA, it has to be really said. So really also someone who really helped to lift women up in this world. And so Cobb and several other women, they really exceeded the specs of men selected for the Mercury program, right? But not much of it was extensively documented in the way of the results of the tests. And so of the 19 women, who underwent the physical and physiological testing, 13 of them, so 68% of the women, passed with no medical reservation. And if we want to actually compare it, 18 of the 32 men who underwent the testing had a comparably, we had 56% success rate. So the women actually had a higher pass rate. But despite all of this, the only publication that resulted from the testing the women published in 1964 after the program ceased to operate. So the report didn't have any data, but it was a lot of anecdotal comments about the women. Now this is one of the images. So we know that during the isolation testing, this is kind of an interesting anecdote, Cobb spent nearly 10 hours in complete sensory deprivation. 2 other women, Rhea Hurl, and Wally Funk, they spent more than 10 hours in isolation. And in all cases, staff terminated the testing, not the testing subjects, right? So at the time, it was thought that 6 hours was more or less the cutoff for tolerance. And for context, the isolation testing for men was pretty different, and they were placed in these soundproof darkrooms for about 2-3 hours. So pretty amazing what all these women were put through, and to really test the limits. And this, however, we didn't really have, again, women didn't go to space then. Jerry Cobb's testing was kept quiet. And a NASA consultant and a prominent female aviator that you can see here, Jackie Cochran, she actually caught wind of the testing of women, and she submitted a complaint about her reservations of women in spaceflight to the Deputy Chief of Naval Operations, who then asked if NASA had made a formal request to test these female candidates. And because NASA was not involved in this testing, they denied that a request had been made, and all the testing was canceled for the 12 other women. Right? So just because there was some jealousy, or, again, there were not a lot of women at the time. So a rather interesting anecdote to have, an antagonist who was a pilot herself. And you might have seen Jerry Cobb's story referenced in a show that is pretty popular, I think, with most space enthusiasts, For All Mankind. This is on Apple TV. So they represented some of the historical figures. Also, two of the women who also died throughout some of these tests. And so, it was pretty cool to see those stories be represented and all of their efforts be honored in all these different storytelling avenues, such as this show that we will show you a little clip from right now, in fact.
You ever flown a jet before? A couple times.
Right, maybe.
I've always wanted to. You're not married? No, but you're so pretty.
You sound like my mother.
Yeah, that can't be good.
It's not. Oh, here comes Janice.
She's carrying too much speed. Told you. She porpoised.
Deke's not gonna like that.
Stevens, you're up.
And now we're going to return to one of the probably most famous female astronauts. Anyone know who she is? Valentina Tereshkova, right? At the time, the USSR. And she became the very first woman in space in 1963. So this is an image of her. I believe she did not fly again after this. She got involved. She is involved in the political world and a variety of other things, but pretty impressive to have flown in 1963 when, again, in the United States, this didn't happen for quite a while. And then she was followed by another Soviet woman, Svetlana Savitskaya, who was launched into space in 1982. And we were still pretty far behind in the United States. So here's an image of some of the very first American women to be astronaut candidates in 1978. So from left to right, we've got Sally Ride, probably the most famous of all of them, Judith Resnick, Anna Fisher, Catherine Sullivan, and Rhea Seddon. Now, Sally Ride, of course, became the first American woman in space in 1983. She even got this commemorative quarter that was issued 2 years ago. I don't know if any of you have seen it around. There were a couple of interesting quarters dedicated to the history of women. And now this is this beautiful image that also contains, that has Cobb on here. So none of these women became NASA candidates themselves or went to space, but they are gathered here to celebrate Eileen Collins' Columbia launch. This was in 1999. So pretty amazing to see all these women supporting, again, all the other women who got to go to space. And Wally Funk, fascinating story. She became the oldest person to go to space on July 20th, 2021 at age 82. Wow. Don't know about you, I don't know that I'd want to go to space at 82. Now, she was flying not on a NASA mission, but on a Blue Origin New Shepard spacecraft, so during its suborbital flight. So she broke a record that was held by John Glenn for 23 years. Pretty amazing story. And now this is just a little image showing you some of the astronauts that have gone up to space. So now we've obviously had many female astronauts. In fact, we have one of our French astronauts, the first French woman in space here, Claudie Aigneret, who is featured in that little middle section. And yeah, we've kind of come a long way since. We've now had 300, so out of 360 astronaut candidates, we had 299 men and 61 women. It's kind of interesting, the division between military and civilian. It is getting closer. We had 212 military, 136 civilians, 191 pilots, and 159 non-pilots. So it used to be that this was really reserved for people who were pilots in aviation. And now, of course, we send people who are in the medical profession. We want doctors up there, of course. We send all sorts of professions. So pretty interesting to see that diversity. And interestingly enough, some of these female astronauts are commemorated on the lunar surface. Now, this is there's a list online that was compiled by Anjali Tripathi from MIT, and of the 1,578 lunar craters that are named after people, there are of course many more craters on the moon. Only 32 are named after women. So we have, of course, very famous historical figures like Hypatia, Caroline Herschel, Maria Mitchell, Nicole Reine de la Brière-le-Put, a French woman who worked on, in the 1700s, she calculated actually Halley's Comet's orbit. And of course, Annie Jump Cannon, Henrietta Leavitt, Marie Curie, and several astronauts as mentioned. So we have Judith Resnick, Kalpana Chawla, Sharon Christa McAuliffe, Laurel Blair, Salton Clark, and of course, there is one woman commemorated who is still alive, Valentina Tereshkova, who has a crater on the moon. Now coming back to our present time, now it's wonderful to see that women are consistently placed into these missions. And so this was when we had 4 women serving together on the International Space Station on April 14th, 2010. And that represented the highest number of women in space simultaneously. So clockwise from the left, we've got Dorothy Metcalf-Lindenberger, Stephanie Wilson, who were both STS-131 mission specialists. We've got Tracy Caldwell-Dyson, and we've got the JAXA astronaut Naoko Yamazaki. So of course, again, it's not just American women going to space. We have a lot of women from Europe, from Japan, from Canada who are getting to go to space. And now this is an image of Christina Koch and Jessica Meir, who performed the first all-women's spacewalk on October 18, 2019. Now this original spacewalk of all women was supposed to be planned a little bit earlier that year in March with Christina Koch and Anne McLean. And there was a bit of a snafu with the suits. There were some issues. I know this made quite a lot of news. You know, people were like, oh my gosh, I can't believe they didn't make spacesuits for women, etc. It was a little more complicated than this, which is that there are different sizes, of course, for the different parts of these spacesuits. And so at the time, they didn't have 2 mediums available. And so that was why it got canceled. Safety is obviously, of course, always the most important part. We want to make sure that astronauts have spacesuits that are nice and snug because for maneuverability reasons, right? But it is worth pointing out that part of the reasons why actually they never made an extra small, and that was the size that most women needed, and they stopped making the small, which was still too big for women, was budget issues, basically. You know, it is the astronaut suits are very complex and very expensive to make. And so that was one of those small little details that did impact, you know, women in space. And now we see Christina Koch again. So this is the crew of the Artemis II that it has had some delays. We hope it'll fly in April 2026.
My question is why is only one woman going on the Artemis mission? You'd think maybe balance it a little bit by now. I mean, it is named after a goddess.
That's right.
Maybe men are just more expendable.
They're the red shirts.
Well,
maybe
that's the right way. Well, but there's some indication that women may actually be better in space, so we'll get to that.
Yeah, this is an interesting point that you bring up, because And I want to bring up this story that actually was to lead into this. This was on Snopes, believe it or not, because there is this comedian actually made a little song about this, and it went viral online. So a lot of people were talking about whether NASA asked Sally Ride if 100 tampons would be enough for 14 days in space, right? So there's, of course, a lot of questions of, health and hygiene in space, and those are very important because we do study the human body in space, and we want to understand how the human body responds to things in space. So she was indeed asked if that was what she needed, and she said, no, that would not be the right number, which I'm sure our female audience right now is probably laughing. But they wanted to be safe. They probably had good intentions. They just didn't know. And so she said, you can cut that in half with no problem at all. They also, by the way, there were pictures of this online. They designed a makeup kit for women early on. Some of them didn't know what to send with women in space. So we have, again, come quite a distance since then. And so we are wondering, is there what would happen if we sent only women to space? What's the physiological aspect? So this is an article that I actually randomly found at the airport. It's from July 19th, 2020 or 2019. I forget the year, but it was in National Geographic, and it's written, in fact, you taught me, I did not know who Nadia Drake was.
Yeah.
Of course, an interesting name.
Yeah, Frank Drake's daughter. Frank Drake was a professor of mine at UC Santa Cruz, of course, famous radio astronomer.
Yeah.
The Drake equation, he came up with that, but Nadia is a science communicator and a great, wonderful science communicator.
Yeah, writes wonderful articles. So she wrote this piece that was very well researched that was called Let's Send Only Women to Space in print, or Here's Why Women May Be the Best Suited for Spaceflight. Believe it or not, that is actually the case, and that's continued to be now an interrogation. And so, we mentioned that there were not a lot of leftover data from all these tests that were done, but we do have some studies. So this was a NASA study. This is a little excerpt from a study from 2014, The Impact of Sex and Gender on Adaptation to Space. So they go through, they highlight how space affects, various parts of the body, various parts of our organism. Very interesting. And this is, again, a continued topic of research. So this is a much more recent study that looks at really a small detail. Now, it's worth pointing out that we have very small sample sizes, right? We haven't sent that many people to space in general, and we haven't sent that many women. So it continues to be a very, very active area of research that's very interesting. But to give you a bit of a summary of why it would actually be a really good idea to send women-only crews to space, we have lighter body mass, right? And when you are sending, for example, a crew to Mars, if we ever do this, that makes a significant difference in the propellant that you're going to send. It makes a significant difference also because we consume fewer calories for the same work, right? I think right now the recommendations are generally 2,000 calories for women per day and 2,500 for men. And so that makes, when you are, again, packing for a very long trip, you'll know this if you've ever taken a road trip or you've packed, you've hiked somewhere, makes a big difference when you're carrying all that weight. Women, of course, have smaller stature, consuming fewer resources, and we have more fat reserves, which also affects, different distribution of fat. And we have, we excrete less. And so that puts less of a strain on, for example, recycling systems for CO2, et cetera. And we seem to have fewer long-term health issues associated to space.
I'm waiting for somebody to talk about, well, you won't grow potatoes on Mars as well then.
That's,
it's not how it would work. But all of these are really great points and make you wonder, maybe that first crew to Mars should be all women. One of the big ones is the lighter body mass. Every kilogram you have to lift into orbit, you've got to burn fuel to do that. And it's a kilogram of something else you can't bring with you.
Yep.
So, Jared, do you know if that's a topic of discussion at all in the space community?
At times it can be, and obviously the mass of your crew is a major consideration for any flight that you're doing. So even something like crew rotation for the International Space Station, if you want to be able to carry up maybe an extra 10 to 15 kilograms of payload. That can all depend upon who's actually on your spacecraft and what their weight is coming up to
There
that
are
flight.
height restrictions. I think I remember that the ESA application had height restrictions, right?
Yeah, so there used to be height restrictions. A lot of that was based on the fact that the Soyuz spacecraft was the lifeboat for the International Space Station, and Soyuz was someone like me who's 6'3" or 1.92 meters in height. You're welcome. Better system. But I'm right on that limit of the height. But nowadays, with things like Crew Dragon and Starliner and upcoming spacecraft that are in the design right now, the heights are several inches more now. So yeah, so there's really not too much of a limit. But I know there's been astronauts who are tall, like Paolo Nespoli from Italy. Yeah. He's a very tall guy. He actually had to basically sign a waiver that said, if I get hurt, I won't do anything bad towards you, Roscosmos. So
interesting. Yeah. And you might have seen an interesting news, which is that the crew for Blue Origin's 11th human flight and is the first all-female ever. So this was just announced. Now again, this is not a NASA mission. They basically bring people to the Kármán line. So we're talking about 100 kilometers, 60 miles to where roughly space officially begins. But it's interesting that they're doing this. I think it's pretty cool. They're sending Katy Perry in space, but they're also sending someone who's an astronaut or who's worked on, I believe, a lot of space missions, Aisha Bao. We've got journalists. We've got a couple of very interesting people on the crew. And so if you want to know more about this, there is a NASA documentary. There's quite a lot of resources. You can go on nasa.gov/women. They're doing all sorts of celebrations, and there is this past, present, and future of women in space that is on YouTube, freely available. But yeah, so it's kind of an interesting history. And in fact, you told me earlier, you asked me, I wanted to make sure I hadn't missed anything, and you told me about an interesting little update that happened recently.
Yes, so we had SpaceX Crew 10 launch for the regular International Space Station crew rotation on May 14th, and the two astronauts seated in the front, Anne McClain on the right there is the commander, and Nicole Ayers over on the left is the pilot. This is the first time in human spaceflight history that the commander-pilot duo has been two women. So that was great to finally have that happen. Finally have that happen.
Cool.
So.
In fact, right now, Jared, it's time for our latest out to launch. You've got some more news for us.
Oh man, we've got a lot of exciting stuff to cover, so let's just jump right into it. We're going to start off down in French Guiana. Yes, thank you, Laura, giving me the good, the A-OK that in French Guiana on March 6th with our Ariane 6 finally beginning commercial service. That's right, Ariane Space has gotten, or is it Ariane Space or is it something else?
I think it's Ariane Espace. I'm not sure, because I think they anglicized the word.
All right, well, Laura said it, so.
Oh no, I'm
so there you go.
Now.
So I believe you the most. But launching a French military satellite, but it's just nice to have the rumble in the jungle, as the commentators used to say with the Ariane 5. With that. So. Moving on a little bit to something that happened a little later that day, but was not as successful, was the launch of SpaceX's Starship Flight 8. Now this happened also on March 6th, and it was a nominal flight of Booster 15 through the first portion of ascent, complete with the third time a booster has been caught by the tower. So, interestingly, these tower catches are starting to look like that they are the actual easy part of flying a Starship Super Heavy, because 30 seconds before main engine cutoff, Ship 34, which is the upper stage, the Starship of the Starship Super Heavy rocket, it had a premature shutdown of 4 engines.
Wow.
And not just that, it lost attitude control, because it turns out the 3 Raptor engines in the center are the ones that provide attitude control, and those 3 were lost. Now, it was a vacuum engine that went out first, if the diagram from SpaceX's webcast is to be believed. And once you only have 2 engines and they're not able to actually move it, that was it. It went out of control. This time, unlike the Flight 7 broadcast, we actually watched it go out of control in Flight 8. So I want to say big props to SpaceX for keeping that stream up and the camera on Ship 34 running so that we could catch it. That also tells us, since they were having imagery come down, that they're also getting telemetry still coming down from it. So hopefully this will help them. Flight 7 actually had a similar, at the similar portion of launch with Ship 33 where their in-flight failure occurred. And there was testing that was done between Flight 7 and Flight 8. Specifically, there was a 60-second test done on the ground in order to try to figure out what it was. They thought it was harmonics, or basically the vibrations of the vehicle sort of shaking apart the engines. Turns out that might not actually be it. And if you think about it, testing on the ground does not give you the same thing as testing 30 seconds before main engine cutoff. So yeah, it's a completely different environment as opposed to doing a ground test. So I guess surprised that SpaceX would make the same mistake twice, but also maybe not, because the test wasn't really something that could have fleshed out a mistake in that time period. It is noting with a leaked image that came out from SpaceX that it did show missing Raptor engines in the engine area after it was still going. So we don't know if those, at least 2 were gone. So one of the vacuum engines on the outer ring and one of the center Raptors in the middle.
We've seen that before though, right?
No, we haven't. At least we haven't seen engines falling off of the vehicle before. Right. So, yeah. So as to what's causing that, don't know. This was the second flight of a Block 2 Starship, their updated Starship, and this was its second failure in a row. So they might need to. They definitely got to work on that testing at the minimum. I think a third failure in the next flight on Flight 9, that you might need to go back and look at the design at that point. I don't work at SpaceX, so I don't know nothing about their design work, but I know if you got it 3 times in a row and it don't work 3 times, you definitely need to look at what you're doing and think.
But the chopsticks are working,
about
right?
it.
I guess those worked every time.
What's amazing is that the hardest, what we thought was going to be the hardest part of working on this, which was catching the booster, is actually turning out to be the easiest, easy peasy lemon squeezy with
There was
the
one
flight.
fail on that, wasn't there?
So they had one where there was a problem on the tower itself, so they decided to do a offshore landing. But it landed upright in the ocean. That was on Flight 6, and it did exactly what they were expecting it to do. It's just that the communications between the booster and the tower were not present, so they did not allow it to come back. But they still did do a precision landing out in the ocean
and
offshore.
That means they have to sort of swap out a program, don't they? Because landing with the chopsticks and landing on a floating thing is probably 2 different things.
The whole idea with the chopsticks is that basically you are bringing the booster back to its landing site, which is going to allow it to be reused near instantly. So essentially we're going to be doing aircraft equivalent checkouts on this. So like basic inspections, fuel it back up, back on the launch pad, ready to go. And they're talking about hours of wanting to do that, but also like you got to fly it a lot before you could get to that point. So, because when you go on a flight, they do inspect your plane before you get on it, but it's the very basic stuff to make sure that at least most of that is going to work out correctly there. So so
pretty amazing.
Good luck.
What's coming up that we should look forward to?
Flight 9 would definitely be it, with another Block 2 Starship on top of it with Ship 35. But they have to go through their own investigation. So the FAA has mandated they have to do a mishap investigation, which is standard. It's what is done in every mishap in spaceflight in terms of launch vehicles and things like that. So this is not out of the ordinary. It's not picking on SpaceX. And then also very important, something that many people, including many space journalists, forget to cover, is that mishap investigation is being led by SpaceX themselves.
Oh, that's
so they do the work and then show the FAA the work, and then the FAA clears all of that.
Are there ever issues of transparency and kind of vested interests with regards to them doing it themselves, or is it a question of resources? Or
so there should not be that. This is being done because of resources. The Commercial Spaceflight Office at the FAA is not exactly a lot of people.
Resources, obviously.
Yeah, and companies are usually, at least in spaceflight, very good about making sure that they're honest about things.
Yeah, they want it to work,
because it's a lot of money at stake, billions of dollars at stake with some of the contracts that these companies are working on. So there's very little incentive to try to hide anything or pull the wool over the FAA's eyes about things.
Yeah.
And also with some recent things that have happened on the aerospace side of the FAA, in terms of allowing companies to investigate themselves or run themselves in certain ways. Those lessons have been applied to the commercial spaceflight office. So, and they're usually spot on. So it's just that in this case, I think it was an issue of ground testing, just not catching what the actual problem is.
Well, thank you for that, Jared. Always fascinating. I love it when we can fit an out to launch into the show. Well, right now we're going to turn to our 90th anniversary feature for this month. It is the 90th anniversary of Griffith Observatory in May, and each month at All Space Considered, we're having a small feature, and we've put together a little movie about the women that have made contributions at Griffith Observatory. Now, I know we've left some people out. I'm sorry about that, but we've done the best we can, and we hope you find this inspiring.
Welcome to all of you. I hope you didn't come here as a consolation prize for last night's game, but we're sure happy that you're with us tonight.
There have been a lot of really remarkable new developments and trends in farming that have been experimented with and supported by the USDA that they're trying to get the word out. And so I supported that effort. So I had the opportunity to learn a lot about soils, which is really cool. So the whole idea is let's get a really healthy microbial system, never till it, that disrupts it, feed them like crazy with all these cover crops. And then at the end of the season, you just flatten everything. So you get like a layer, like a 6-inch layer of everything just rolled over.
Changes that we have seen in Earth's history have been spread out over hundreds of thousands of years, millions of years. That's the rate at which the globe changes, and the life on that globe, on Earth, adapts to that rate of change. There's no time to adapt. This is happening so quickly. And yes, there have been high global temperatures, but what hasn't happened before is this crazy, crazy rate of change. It's happening in blink of an eye in geological timescales. As I said earlier, scientists are very conservative. They'll always say just the barest minimum. So when you get scientists saying, no, this is related, that is something to take note of. So when you look at the cost of fighting, for example, these fires, not even to mention in terms of human life and rebuilding and so forth, it would be unwise to turn our backs on it. I urge you to look at different candidates' positions on some of these things and think about the change that you want to see. You may not realize that there are things you can do, tangible things, reachable things. This is solvable.
Okay, so that means they hid. They rewrote, they put a little quick patch in the code, made sure that the computer didn't see the temperature of the engine nozzles until T-minus 30-ish seconds.
Hello, and welcome to your Pretty Pictures and Solar System Weather segment from September's All Space Considered. This first image here is the spinning pulsar of the Crab Nebula, which combines the X-ray from Chandra, visible light from Hubble, and the infrared from Spitzer. In this beautiful image, the center here is a neutron star that's spinning at 30 kilometers a second.
Hello everyone, and welcome to the March 2025 Sky Report. My name is Vanessa, and I'm joined today by Patrick.
Hi everyone.
Let's see what's happening in the skies this month. On March 6th, the moon will pass in front of the bright star Elnath in the constellation of Taurus, in an event called a grazing occultation. Here, zoomed in, you can see that the very edge of the moon will come in contact with Elnath at 8:49 p.m. for us in Los Angeles, according to the International Occultation Timing Association. It will reappear at around 8:57 p.m. These times are very dependent on your location on the Earth, So being even just one city over can make a difference. So if you'd like to see this in Southern California, start looking with binoculars at around 8:40 p.m. so that you don't miss it.
Sarah did such a great job of introducing us to Arecibo, particularly the most recent work released, including how Arecibo even helped with the DART mission. So Arecibo has actually been one of the most productive telescopes in our observing arsenal, particularly for rocky bodies out in the solar system. It's been responsible for collecting data of over 850 near-Earth asteroids, and it's also allowed us to further resolve other aspects of these bodies like sizes, the shapes, the spins, and even their surfaces.
The dragon is on the moon's case tonight. And just as people in the past assembled to make noise in order to chase the dragon away, we too tonight are going to make our best effort to ensure that the moon remains safe. It does require, of course, a considerably difficult task.
All Space Considered producer Haley had an opportunity to interview graduate student Krista DeCursey at Stewart Observatory at the University of Arizona last summer. We're pleased to finally bring you this excellent interview.
All right. Thank you so much, Krista, for joining me today to talk about your recent work with the JWST Transient Survey. Do you mind introducing yourself a little bit for us?
Yeah, of course. My name's Krista DeCursey. I'm a University of Florida alum, and I'm in my 4th year of graduate school now at the University of Arizona, working on my PhD in astronomy and astrophysics. And I work with the JWST collaboration. It stands for the James Webb Space Telescope Advanced Deep Extragalactic Survey. It's a galaxy-based group studying the most distant galaxies out there with the James Webb Space Telescope. But I do slightly different work. I study exploding stars, which has led to a bunch of great opportunities, which I will talk about today.
Awesome. Thank you so much for your time. So can you explain a little bit more about the objects you set out to find?
Yeah. First, I'll describe what a transient is versus a galaxy. A galaxy is like the Milky Way. We reside in the Milky Way galaxy. It's a large collection of stars that exists as an isolated object. Sometimes it combines with other galaxies. Transients, on the other hand, are any sort of object that appears and then disappears. So something like an exploding star appears just as a star at first, which if it's in a distant galaxy, we wouldn't be able to see that, maybe not even with a telescope. But once it explodes, it can outshine the entire galaxy, and so it's transient in nature. It changes significantly with time. But yeah, transients and galaxies, very different things.
Okay. So where in the sky did JWST look for this survey, and why?
So the JWST collaboration looked at a patch of the sky called Good South. Good South stands for the Great Observatory's Origins Deep Survey. And there's 2 patches with the GOODS survey. It was one in the north, GOODS North, one in the southern hemisphere, GOODS South. So we picked this field because it's a very well-studied field. Pretty much every telescope that exists has looked at this field to characterize the galaxies. JWST looks at near and mid-infrared light, and so we'll be able to see this field much deeper in a different wavelength of light, and we already have information about these galaxies that will allow us to make larger leaps with this new data than what we could have previously done. And we lucked out. So the JWST survey was designed as a galaxy survey. Having cadence between observations doesn't really matter with galaxy surveys because they don't really change in the course of a year like a transient would. But Space Telescope Science Institute, which schedules all of the JWST visits, decided to break up the observations over a course of a year, which allowed for my project to happen. If it was all taken at the same time, I would have no baseline for any sort of change in this field. And so we got 2 very deep images of this well-known patch of the sky taken a year apart to where I could look at the 2 images and find the things that appeared or disappeared or things that changed in brightness. And that was the basis of the project that I worked on. Upon finding all of the supernovae, the exploding stars that either appeared or disappeared in one image versus the other over the course of the year, we were able to specifically target those supernovae that were still visible in the second image to get follow-up images to see how quickly they faded, which helps us characterize what type of supernova it is.
So you mentioned that you could, in that follow-up imagery, you could kind of interrogate those signals a little bit more.
With the follow-up that we did, we submitted I think it's called a Director's Discretionary Time, DDT, proposal. Based on our preliminary analysis of those first 2 images, we thought we had some pretty distant Type 1a candidates, a type of supernova that allows us to do some cosmology and figure out different things about the expansion of the universe, which would require follow-up observations to confirm their Type 1as and then proceed to do that cosmology. And so we had a strong argument to get follow-up observations, and we did. The proposal was accepted, and we got 2 more sets of NIRCam images over the course of the following months to give sufficient time for these objects to fade so we could characterize it's called a light curve, how quickly they brighten and then fade. But we also used NIRSpec to get spectra of a handful of the most exciting candidates that were distant and bright, which led to 2 separate papers, and a 3rd paper will be out soon, and potentially more papers for just these very distant, interesting objects.
That's pretty impressive that in just a few images and a follow-up that you're able to generate that much data for the community. What are the important implications of this work?
Yeah. We always knew that supernovae existed at these distances. We just didn't have the facilities to discover them yet. So it confirms there's supernovae at these distances. But the more exciting thing that's still to come is the rates at which these supernovae are exploding at these distances, which is a bit more unclear. When we look at objects that are very distant, it took the light that many billions of years to reach us. So if the supernova exploded when the universe was 1 billion years old, the universe is 13.8 billion years old. We're looking at light that's 12.8 billion years old. It took the light 12.8 billion years to reach the James Webb Space Telescope. And so we're getting a view of the universe when it was in its not quite infancy, but early childhood stage. And what's special about looking at supernovae at these distances is that that's our only view of individual stars. We found many more farther away galaxies than these, supernovae that exploded when the universe was 1 billion years old. We're finding galaxies that were existing when the universe was a couple hundred mega years old. But those are collections of stars. We can't study the individual stars in those galaxies. This is the opportunity to study the individual stars, and studying them when the universe was 1 billion years old as opposed to the 13.8 billion years old it is now. It tells us how the universe evolved and what kind of explosions enriched the gas that made up the galaxies, because these explosions of stars is what allows all of the elements to be flung out into the universe, like the carbon that we're made out of, the oxygen that's in the water that we drink. All of those elements were built in stars and were put out into the universe because of these explosions. And so these early explosions tell us how these chemical abundances arose.
Awesome. Thank you so much. Your work is really interesting, and looking forward to the multiple papers that are sure to follow this one.
Yes, lots in the works.
Awesome. Thank you so much, Krista.
Thank you.
And now for our final feature at All Space Considered. Laura May, you're going to lead us through a mission that just ended, but it was going on for several years, and it actually, it mapped the Milky Way, as people like to say.
People have been looking at it for as long as humans have been around. We can't do this as much anymore from obviously the Earth because we have so much light pollution, but there is a lot to be studied. And this mission, so the Gaia mission, this is a European Space Agency mission called the Billion Star Surveyor, and it was actually launched in 2013. So it's been up there for a little while now. Launched on what kind of rocket, Jared? I'm sure you can tell me.
An Ariane 5.
Obviously, French technology that launched it. Now going back to, again, our Milky Way, and there really is quite an amazing history to our study of stars, and more specifically to what we call astrometry. Now, Astrometry, is really one of the fundamental components of astronomy, and it is thousands of years old. It actually dates back to long before the invention of telescopes, and it's one of the first sciences developed by humankind all over the world. So our first records of systematic astronomical observations, they date back to the Assyro-Babylonians around 1000 BCE. Now this was in present-day Iraq. And we also have this beautiful image. So this is the 10th century CE Greek copy of, and I may butcher the name, Aristarchus, you got it perfectly. I could say it in French, but Aristarchus of Samos, the 2nd century BCE calculations of the relative sizes of the sun, moon, and earth. So you can see what he attempted to do. He tried to measure the distance of the sun and the moon from Earth by measuring the angle between them when the moon appears exactly as 1/4. So with the help of trigonometry, he determined that the sun is 18 to 20 times more distant from Earth than the moon. So he wasn't exactly accurate. He was a little bit off by a couple of factors, but for the time, that's pretty incredible, right? And he had the right idea on how to do this. Now, of course, now we know the sun is about 400 times more distant than the moon, but again, it's pretty amazing that way back then they were already trying to calculate positions of objects and really doing what we call astrometry. So this is to show you really how we can measure this kind of rudimentary way we have of measuring distances through stellar parallax. And so you'll see we have the Earth is of course at a different part of our orbit when you go 6 months later. And so from there you can use a star and you can measure where the other stars have shifted, right? And in fact, you can do this yourself. I'm using our little Einstein statue as a guide. Of course, he's actually pointing to something else if you've ever been down to the Gunther depths of space.
Yes,
but,
the bathrooms.
But you can basically put your finger right in front of your face. This is a classic example. And then if you close one eye and then close the other eye, you will see your finger at a different position with the movement behind it of different objects. And so this helps us understand really how stellar parallax works and how you can estimate distances of certain objects. And of course, you can try it yourself also. If you're very close to your face, you will see a very big difference when you switch eyes. But when you go much further away, you will have a little less of a difference, right? So that is something to take into account. It is much harder for us to measure the positions, velocities, and get all of these little details about stars the farther away they are. And now again, all of this was used and compiled in catalogs over centuries. If you visited us, you might have seen our wonderful meridian arc. In fact, we're at local noon right now as we speak. I believe it's 1 o'clock. Yep. So we just hit local noon, so you can come here any day when it's sunny and when we're open and see the sun's transit across our meridian arc. And an arc much like this one, it was about 10 times bigger than this, was used by someone in Uzbekistan in the 1400s, a man called Ulugh Beg. And he used it to map the position of about 992 visible stars at the time, and he created one of those very first stellar catalogs that was so important to astronomy. So here we see a little bit of a history of our mapping of the heavens and of stars, and of course it got more refined in time, and then we have a jump in technology that allows us to do things much, much more precisely, right? And part of the reasons we need to measure things and we need to understand all of these stars is that it helps us measure our place in the universe, and it helps us understand what objects are, right? So this is to show you the classic VAR plate. I'm sure everyone here familiar with the VAR plate. You might have seen it. It was exhibited recently at Lockman. In fact, I think it's a reproduction at Carnegie if you ever visit Carnegie. I can't remember if they have the actual real one out. It's very small. I was surprised by how small it is.
Yeah.
But this was a plate, very, very famous glass plate. This is how we used to do astronomy. And Edwin Hubble worked on this, and he noted that little variable star there. So this was a Cepheid variable. This is a star which brightens and dims periodically, and whose period, so basically how often it pulsates, is directly related to its luminosity or brightness. And so thanks to having spotted this variable star, we were able to understand our place in the universe. Pretty remarkable. Now, going forward in time, we have the Hipparcos mission. So this was really the predecessor to Gaia, and it was launched in 1989 by an Ariane 4 rocket, once again. And the mission was active until about 1993. So it lasted quite a while, and it measured 120,000 stars. I remember being in school, in fact, and we had the Hipparcos catalogs. And when I was first starting out, I remember thinking, oh, this astrometry, this is kind of a boring class. But then as you dive deeper in astronomy, you realize how important all of this is, and that really the amount of things you can do with this data is pretty remarkable. And that's one of the really cool things we're going to talk about, is what this Gaia mission can actually do with all of this data. Now first, this is how Gaia is observing the skies, right? So we've got astrometry, which we just spoke of. So we're able to identify the proper motion of stars. And then we've got photometry. We're getting all sorts of details on color, on mass, on temperature, age, brightness. And then of course we've got spectroscopy, which is nowadays done by most space missions. So we're able to look at the spectra of a variety of these stars and get a lot of information from this. This is to show you also the reach of this mission. You might have, perhaps some of you may have seen the Kepler mission had a nice little map that showed this little circle of where it was looking for exoplanets. It was so close to home, actually. I think people often wonder, oh, well, are we looking, for planets in other galaxies? Are we finding, what do we know? And really, it's worth understanding that our home galaxy is where we can do the best research and where we can find the most important information, because it's right there. But of course, it is very hard. We are inside this house and we're trying to figure out the layout of this house, right? So this shows you how that we are looking quite far into the Milky Way. This is much farther than, for example, a mission like Kepler that was hunting for exoplanets. There is quite a lot of reach with the Gaia mission. And of course, the Gaia mission has worked in conjunction with quite many other telescopes, right? Many other missions. So there was a collaboration. They combined NASA's Hubble Space Telescope and Gaia to obtain the most precise measurements to date of the universe's expansion rate. So this is done by calculating the distances between nearby galaxies. We use these special types of stars that we mentioned, those Cepheid variables, as our cosmic yardstick, and we can compare their intrinsic brightness as measured by Hubble with their apparent brightness as seen from Earth. And so we're able to calculate their distance, and Gaia can further refine this yardstick by geometrically measuring the distances to these Cepheid variables within our Milky Way galaxy. So this really helped us to calibrate all of these distances, and it's really, really fundamental astronomy. Now, what's interesting about the Gaia data is that it is released in packages, right? It's been pretty exciting. I feel like for people who like video games, this is like we're waiting for DLCs. I was thinking about this last night. Yes. You get these releases, these extension packages. I don't know if they would like me comparing it to
That
this.
is a great way to put it.
But it is. It's the DLC of the Gaia mission, because so the data packages will come to an end, and in fact the spacecraft will come to an end as well. So officially, it shut down operations on January 15th of this year, 2025. It completed its whole sky scanning mission. This is all planned in advance, so it's a little bit different to a mission like the James Webb Space Telescope, where people submit proposals and then they're accepted or not. This was a little bit different. It's planned, but in fact, January 15th is not technically, you were mentioning, Jared, the official date?
Yeah, the official passivation and deactivation of Gaia will be on March 27th. So that means that they are going to have all of the fuel go out, any of the propellant from the reaction control system vented out, and then shut down every system, and especially tell it shut down your radio on March 27th. So,
is there a Gaia 2 planned?
We're going to get to that.
Okay.
That's a very good question. I'm so glad you asked this. Let's go back to the DLCs, in fact. So those data releases, those amazing data releases, so we've had 3 so far. We are expecting a 4th soon-ish. later this year or in mid-2026. And the last one, the very last one, the 5th data release, that will drop at the end of the decade, and that will be the big one, right? So it's going to include 10 years of very high precision data. It's going to be monumental, and every single one of these data releases has different information, different studies that come out as a result of this. So we'll have to do another All Space episode, All Space Considered, in 5 years. I hope you all, it might be us, it might be other people who will talk about this. Now I want to go back to some of the incredible data that's come back from this. So if you visited us at Griffith Observatory, you might have seen in our Amundsen Hall of the Sky, Our Sun is a Star exhibit, and you will have seen our Hertzsprung-Russell diagram, right? So this is a fundamental tool to study populations of stars and their evolution. I suppose a lot of kids learn about this in school in America. Do you guys see it in school?
Not in primary school, I will say. In college, yes.
Although I guess kids who visit us on the school program, they get to learn about this diagram and how to interpret it. And so it shows also this large diagonal stripe across the center of the graph that we call the main sequence. And this is where all of our fully fledged stars that are generating energy by fusing hydrogen into helium, like the sun, are found, right? And then we've got our massive stars, which are bluer or wider colors, and they're usually found at that upper left end of the main sequence. And then we have our intermediate mass stars, again, like our sun, that's more towards that little middle, characterized by those yellow colors. And the redder low mass stars are found towards that lower right. So a very, very important diagram to astronomy. And so Gaia was actually able to recreate a Hertzsprung-Russell diagram updated with some of the most up-to-date information on stars. And it's pretty remarkable because we have some more elements, right? So within this one that you see, we've got more than 4 million stars that are within 5,000 light years from the sun. They're plotted on this diagram with information about their brightness, color, and distance. And this is from the 2nd data release that happened. And they're plotted according to their color on the horizontal axis and brightness on the vertical axis. And they're grouped in different regions of the diagram, depending mainly on their masses, their chemical composition, ages, and stages in the stellar life cycle. Now, it's worth a note that the color that we see in this image, I know it looks a little bit different to what we're used to seeing. We've got a little more colors usually, and they don't represent the color of stars, but it's actually a representation of how many stars we have plotted in each portion of the diagram. So the black is representing the lower number of stars, while the red, orange, and yellow is the increasingly higher number of stars, right? And so we can really see this huge leap from Hipparcos to the Gaia data, especially in the white dwarf region of the diagram. For anyone who's kind of familiar, usually we have that tiny little section at the bottom with just a couple of little white dwarfs. And we also now have more data on the extremely faint red dwarfs, as well as, it looks a little like a fish, so one of those little tails up top shows us on the right that little red clump, what's called the red clump of red giants. So we're seeing a lot of newer elements to this, and we're seeing newly formed white dwarfs. So that's why we have that little arc on the bottom left that's extending all the way up. It's pretty unique to get to see this. And so again, Hipparcos had only obtained reliable distance measurements to only a handful of white dwarfs, but there are more than 25,000 in this diagram. So it's a remarkable leap. I'm sure the people who work on white dwarf stars are delighted. And we were able to see these two little structures. So you can see these two little lines here, the roughly parallel yellow lines within that broader strip. And so we think this is the imprint of two different types of white dwarf stars, those that have hydrogen-rich cores and those that are dominated by helium. So again, really important stuff. And the 250,000 stars that were plotted from the archives of the Gaia, Gaia data, revealed also a previously unseen feature. So you might notice it's a little hard to see it, but there's a little stripe. I don't know if everyone else can see it right in the middle, in between those dashed lines. And we have some stars that are missing. We have an underpopulated section of space here, of stars rather, And it's right in the middle of the M-dwarf regions, and we think it might be related to a known transition in the mid-M dwarf, right? From larger stars that are mostly convective with this very thin radiative layer to smaller stars that are fully convective. So they're proposing, some researchers have proposed that the missing stars in the gap could be due to subtle changes in structure that occur at this transition between the partial and the full convection in these M dwarfs. But yeah, there's a lot to look at, a lot to analyze. We could spend all day on this, looking at this HR diagram, but we'll move on to binaries. So the Gaia mission was very instrumental in, thank you for laughing or coughing, we appreciate you. So it detected binaries through light curves, right? But we've got a couple ways of detecting this. So on the left here, you are seeing these different light curves. So these eclipsing binaries are passing in front of each other, and we've got a different light curve. We can also see, of course, the Doppler effect on our spectral lines that are moving that show us this wobble. And we can also see movement through astrometric measurements, right? So that's that lower little image. So it's pretty remarkable now that we are able to get much better information through Gaia on all the binaries out there. Again, we think a very large proportion, perhaps the majority of stars, might be pairs. They might be binaries. And this is a beautiful, beautiful little rendering. It was in fact inspired, for anyone who knows the Kepler missions, there was a Kepler Ori that was done. I don't know if anyone remembers, there were these beautiful little images of all these little orbits of all these planets that were found. And so they made this wonderful little diagram, I'm not sure what to call it, this little image. You know, stars are social. They're just like us. They like to live in these large groups. And so with this data release 3, we had this comprehensive data that a lot of astronomers had been hoping for that included about 800,000 binary stars. So this animation is basically illustrating the sky projected motion of these binary stars whose orbits have been determined by Gaia. So each little ellipse corresponds to one of those 335 systems that are located within about 160 light years from us and that have periods shorter than 1,000 days. So these are cases where Gaia sees only the motion of one source, which would correspond to the reflex motion of a star due to the gravitational pull of an invisible companion, right? So by the way, the orbits are shown to scale. And they're ordered by increasing distance from the sun, from top left to bottom right. And if you see a line, that's something that we're seeing edge on. So pretty neat representation. And that's one of the cool things. I don't know if you guys have seen any in the news, but Gaia really put some effort. I think that because they were not necessarily a beautiful pictures image like the James Webb or like Hubble, they really put a lot of effort, I think, into their graphics, into their releases to always have these beautiful images. And now we come to Einstein crosses, right? So this is an example of what we call gravitational lensing. We are actually seeing faraway objects, quasars, for example, that get multiplied, right? Their light is bent by mass. So of course, these are called Einstein crosses, named after Einstein, who I believe was the first to note this effect. In fact, he was the first to do an experiment with an eclipse to prove that, of course, mass does bend light. And so these Einstein crosses that you're seeing, those are pretty rare. And we've only discovered about 50 of them, where again, we've got triple images of the same object that we are able to see from far away. And it is very hard to find new ones because we don't know where we're gonna find them, right? We can't calculate exactly where they are. So it's pretty remarkable that Gaia was a big game changer for this. It was able to survey the entire sky every few months with unprecedented spatial resolution. And so we've got these 12 newly discovered Einstein crosses that basically increase this number by 25%. So pretty remarkable. So this is to show you how exactly this works. So we've got a background quasar. In the foreground, perhaps we've got a galaxy. So again, a massive object. And from our vantage point, that galaxy is bending that light, and we are able to see this. It acts like a lens. And yeah, predicted by Einstein in 1912, and now we use it for so much research. So pretty amazing stuff. Now, since we were talking about quasars, Gaia also worked on black holes, right? Now we've got right now about 50 confirmed or suspected black holes in our galaxy. Now this is a little bit different to what's at the center of our galaxy, our supermassive black hole. We've got these other black holes that are smaller, much smaller in mass, but we think, the theory certainly predicts, that there should be a hidden population of thousands or millions of them due to the number of stars that have likely already died over the galaxy's lifetime. And so Gaia has found several of these black holes. So here it's showing you roughly where they are. Of course, we're looking at the Milky Way as edge on here. But this is to show you it found the nearest known black hole, Gaia BH1, so that's what they're calling them, Gaia BH2 or Gaia BH3, and it was discovered in September 2022, and it is 1,560 light years away from Earth in the direction of the constellation Ophiuchus. People often ask us, I think especially, I don't know if you get asked this, children are always, they want to know, are we close to a black hole, and is a black hole about to devour us? So the answer is no. In fact, the nearest star for comparison, Proxima Centauri, it's about 4.24 light years away. And again, this black hole closest to us so far that we found is 1,560 light years away. So it's some ways. You know, I don't think we're at any danger. 300 times farther.
I think we're gonna have to call Rush and Muse and tell them to get to update their songs.
Right, exactly.
So,
they should, really. You know, sometimes you get irritated by songs that are not scientifically accurate.
Yeah.
I think that should be done. So this is to show you an example. So part of the reason they're so hard to find, of course, is that these are black holes. We don't really see them a lot of the time, especially when they were dormant. So many of these black holes that were found were dormant. They are not consuming any kind of material. They're not shredding apart stars. So we have to find them through objects that are orbiting them, right? So we are found, so this is an example of an orbit. So this little black hole, I believe it's BH2, it is orbited by a red giant, which has an orbital period of about 3 years. And again, it is dormant, so much harder to detect than the very bright X-ray ones, right? And in fact, I'm gonna talk a little bit about, you know, a unicorn that was found. I never thought I would hear black holes referred to as unicorns, but we love unicorns. So they indeed found this amazing black hole called BH3, and it is a unicorn because it's the most massive stellar black hole found in our Milky Way. Now, Cygnus X1 that you're seeing in comparison here, this was the first black hole ever discovered in 1964, formed from the collapse of a star, and the second closest known to Earth, but it is, and I enjoyed, there was a quote that called it a pipsqueak, in contrast to Sagittarius A star, of course, our supermassive black hole, which is 4 million times the mass of the Sun, 200 light years away in the direction of the constellation Aquila. We have this amazing BH3. And it's actually very hard to explain why it's so massive, right? So they do generally form from the collapse of a star and the expulsion of much of its material. And that is why they are limited in size. So there are a couple of theories now. It might come from a very low metallicity and thus much older star. Its companion is a very metal-poor object, and the couple are orbiting in the opposite direction to the current of stars in the galactic disk. So pretty interesting, because not only does this give us really interesting information on this black hole, but we think it may be part, so that entire little stream of stars might be part of a disrupted star cluster that was torn apart by the galaxy a very long time ago. So this black hole will certainly be followed for a very long time. Now, talking about, I know, this is great, right? I like how you all get to be surprised by some of these images. There are obviously so many studies that have come out, and you know, in fact, little known tradition, there is a 1st of April, an April Fool's tradition, to put out some amusing papers, some sort of prank papers. This is not one of them.
Yeah.
This is a real paper that was called The Poor Old Heart of the Milky Way. And it is a study on the formation of our proto-galaxy done
name.
with all this Gaia data, right? So they used a neural network to extract the metallicities for 2 million bright giant stars in the inner region of our galaxy. And we think that the central metal poor stars probably predate the oldest part of the disk, right? Which implies that they formed, we're thinking at about a redshift Z inferior to 5. And so this is what forged the proto-Milky Way. So pretty amazing result. Again, it's very difficult to study the heart of the Milky Way, but they wanted to learn whether the bulk of these stars are a tightly bound proto-galactic population rather than stars that could have been accreted from more distant satellites and interactions. So they're arguing right now with some of this data from Gaia against an origin through accretion from a once distant satellite. So more results to come. And now we come to the late night snacks that our galaxy has been having. In fact, we were discussing with one of my colleagues whether a galactic sausage is a technically veggie sausage, because if there's only plant life there,
it's vegan.
It's a vegan sausage, right? So believe it or not, there is a galaxy called the Sausage Galaxy, or Enceladus. It's a pretty great name. They actually named it, there's some interesting diagrams where they say it looks like a sausage because of the direction. And I'll admit I had a hard time seeing it, but it had more to do with the velocity of the stars. So we had we had a collision with a giant sausage galaxy, basically. And it did actually it did damage the Milky Way's disk quite significantly, which would have had to regrow. And I really enjoyed this quote. We do have sometimes a good laugh with some of these studies. And we know that this was what was intended when they name things in this way, right? No one with a straight face can talk about this.
We're talking about it.
We're talking about it, right? So. But they were quoted as saying that there was sausage debris.
Is that the actual quote?
It is the quote. Scattered around the galaxy, but especially close to the center. And that is where it created the trademark bulge. So, people like to have fun in astronomy, and I think that's great that they gave it this name. It's easy for people to comprehend these kind of massive objects and having interesting sizes and interesting shapes in space. So we're grateful to all the people who are injecting humor into this. So this is to show you the merger and the way that this would have.
Not just the merger, it's the sausage merger. Mm-hmm. So we got to get it right.
We got to get it right.
Talk about it.
We got to get it right. So again, our Milky Way. We think our Milky Way has already eaten about 6 galaxies, probably little ones, but this is one of them. So this is to show you the way these mergers happen. And of course, if you come visit us, you'll see on our big picture in the Gunther depths of space, we have some beautiful galactic mergers. Now, something quite interesting, if again we're looking at these galaxies, is that we've got a class of stars called hypervelocity stars. And these are stars that are going very, very fast. They're the fastest class of stars. And they are thought to start their life near the galactic center and then flung towards the edges of the Milky Way via interactions with the supermassive black hole, for example. Mm-hmm. And so there is a team that was searching for these high-velocity stars being kicked out of the Milky Way, and they were very surprised to find instead these stars were sprinting inwards, maybe from another galaxy. And of the 7 million Gaia stars resolved with these full 3D velocity measurements, they found 20 that could be traveling fast enough to eventually escape from the Milky Way. So maybe these, stars, the intergalactic stars, are coming from the Large Magellanic Cloud, this relatively small little galaxy that orbits our Milky Way. They might come from a galaxy even farther. They may have once been part of a system that was flung towards the Milky Way. So it's pretty interesting to look at all these stars and have these curious results that we're able to now get a lot of details on. Now, this is one of many amazing maps that was again created by the Gaia mission. We'll just go through it briefly. But this is a map that shows us the speed at which more than 30 million objects in the Milky Way mostly stars again, are moving towards or away from us. So we call this radial velocity. You might have heard this term in the context of exoplanets, for example. We did use radial velocity to find exoplanets as well. And we can see how the objects are moving over a large portion of the Milky Way's disk. So it gives us a really big picture idea of everything in our Milky Way and how this giant system is working, right?
What do the colors correspond to in terms of direction and speed and all of that?
Yes, so I believe we've got the bright areas that are moving away from us and the dark areas are moving towards us, right? So it's also interesting because you have several objects where the radial velocity differs from that of the close environment. So lots of further analysis to be done on all of this. And you can in fact see the aforementioned large and small Magellanic Clouds, often called the LMC and SMC. At that very bottom, these are these bright spots in the lower right corner of the image. And we can even see, in fact, I believe the Sagittarius Dwarf Galaxy, it's a little vertical stripe. Oh yeah, it's that little vertical stripe that we're seeing right at the center, right below that kind of galactic center. We can see a couple of globular clusters as well, appearing as tiny little dots. So really quite a lot of information when you get to look in detail. And this is to give you an idea of some of the other maps, of course, that were generated. So we've got our radial velocity and proper motions. It also mapped out dust, interstellar dust. Very, very important, right? Yeah. So it tells us what is in between the stars. So the space between our stars, it's not empty, right? It's filled with a lot of dust and gas clouds out of which stars are born. And through the precise measurement of the star's position and their dispersed light, Gaia has allowed us to really map the absorption of the starlight by this interstellar medium. So this map is showing us all of that interstellar dust that fills the Milky Way, the dark regions in the center of the galactic plane in black, and those are the regions, of course, you might have seen it if you've yourself looked up at the Milky Way. I'm sure you've seen it when doing astrophotography, right? And that's where we've got really a lot of dust inside at that very center of the Milky Way. And we've also got a chemical map, right? So we want to know what these stars are made of because that tells us about their birthplace and their journey afterwards and really about the history of the Milky Way. So we also are getting all this information, and all of this information can be complementary to each other, really quite a lot to look at. But coming a little closer to home, this is a really neat one that they released more recently. So this is the position of each asteroid, all of our nearby asteroids here. Oh. Pretty neat, right? Yeah. I think a lot of people didn't know they were also doing asteroids. It's not just stars. So they can plot, this is their position on June 13th, 2022. So each asteroid is this little segment representing its motion over 10 days, right? So the inner bodies are moving faster around the sun. That's that little yellow circle at the center, and the blue represents the inner part of the solar system where our near-Earth asteroids, some of them are Mars crossers, we have our terrestrial planets. Pretty remarkable achievement. And here is another one that actually shows some asteroids that were discovered by Gaia. So of course confirmed through other methods as well, but you can see those three little circular orbits here. We've got some discoveries that were made as well. So those are coming within about 1.3 astronomical units to the sun and very, very nearby. So pretty remarkable. Now most of the asteroids, again, that Gaia detects are already known, but every now and then we can see some that don't match any existing data, and so they got to plot this. And it also, what'd you say?
Very artistic.
It is very, they've really, I feel, put a lot of work into making all of these visuals very artistic. And now we come to something very exciting that it contributed to as well. So it was able to demonstrate that about 352 of those asteroids that it observed have moons, right? So this is an image of Dinkinesh. I think this was about 2 years ago or a year and a half ago that we realized it was shot by by the NASA Lucy spacecraft, and so we can see that little moonlet there. I'm not sure, would we call them moons? Would we call them moonlets? Again, we opened that can of worms earlier.
I was asking about the diameter that would define moonlet.
Would it be a dinky moon?
I like it, a dinky moon, Dinkinesh. And yeah, so in fact, nowadays I think a lot of them get referred to as binary asteroids, right? In fact, I think the DART mission Was it considered a binary asteroid? It slammed into Dimorphos.
It slammed into, there was a smaller asteroid orbiting a larger asteroid, and the smaller asteroid, they changed its orbit and proved it.
So pretty interesting objects that can really tell us a lot about the history of the early solar system. Now, the Gaia mission, in its early, advertisement of sorts, or in its early, when people were discussing it, we spoke a lot about exoplanets. Would it be able to find exoplanets? In fact, so long before we had found exoplanets, we had a lot of discourse around cosmic plurality, the plurality of worlds, and so a lot of people were trying their hand at finding exoplanets. And Herschel, known from the discovery of Uranus, in fact, we just celebrated its discovery day on March 13th, and so he speculated about an unseen companion that might have been affecting the binary star system 70 Ophiuchi, right? And originally, so we used this astrometric method. Again, we're detecting this little shift in position, and it was used to characterize binaries, right? We can measure this little oscillation of stars and their movements, and so many thought they could use this to detect the influence of unseen planets. So in fact, in 1855, this is a real publication authored by Captain Jacob from the Madras Observatory, and he focused his attention on that very same star that Herschel had looked at, and the discovery of a planet was published in the Royal Astronomical Journal in June 1855. Now, of course, this was then either retracted or it was, we didn't have quite the means to prove this at the time, but I believe since then we've actually have found a planet that was around that star. I don't know if they used the previous, that previous data and verified it, whether they were right or not, but pretty remarkable that this was published then and that they had already thought of using astrometry. Now, some of the estimates that were out at the time, right after Gaia's launch, suggest that they were about 21,000 exoplanets out to about 500 parsecs, so that's around 1,600 light years, and that's about what we would detect using these astrometric measurements from the nominal 5-year mission, right? And it's true that we haven't really seen that in the news, right? Other missions have continued to make discoveries, and Gaia hasn't released a lot about exoplanets. So this was one that was found. So they did find a little bit of a wobble in a star. It was confirmed by Gaia and Hipparcos data. And so this was announced in 2023. They believed that basically the star was hosting an exoplanet, and it was later confirmed by Subaru. So this was the Subaru telescope that was able to image this. But we did have, in February 2025, the first official confirmed astrometric Gaia planet. And so it used 3 other ground-based telescopes to confirm it in Texas, Arizona, and the Canaries. And it got called Gaia 4b. And it's a relatively cold gas planet that orbits the star Gaia 4. So this is an artist's impression that visualizes a portion of the planet's orbital motion as determined by, of course, all that astrometric data. So why hasn't it found more? That is a question. We have had some changes in the past decade regarding, we know much more, of course, about exoplanets. We've also refined the occurrence rate of giant planets in the past decade, thanks to many other surveys. And of course, the astrometric method works a little bit differently than, for example, radial velocity and things like that. And it is much more sensitive to far away planets that are very large, right? We have other methods that are better at finding close-up planets, very close to their stars. So we will have to wait for future releases. There are some rumors floating around that perhaps there will be some exoplanets in the data release 4. It'll be interesting to see kind of what they come up with. But again, even when we don't find something, it's all very interesting to science nonetheless. It tells us something, right? And even closer to home, we were able to get some information, some new knowledge about our closest star, the sun. So we're going back, in fact, to that little HR diagram that we showed you earlier, and that little main sequence. And so we have where our star is now and its evolution, right? So we can't really study our sun in the same way as other stars. It's really close to us, it's really bright, But what they did is that they identified many, many stars that had similar mass and composition, but had different ages, so that they could create this full sequence of a sun-like star's lifespan. Amazing, right? So they were able to really refine and give us more information about our own sun and how it's going to evolve in the future. So we know that our sun will reach a maximum temperature at about 8 billion years of age. Then it's going to cool down and increase in size, and it will become a red giant star around 10 to 11 billion years of age. So I think it's pretty remarkable. There was this wonderful quote by someone who, an important part of the Gaia mission, Dr. Orlag, who said the Gaia mission has touched everywhere in astrophysics. And I think that's a good kind of way to look at really, hopefully this has shown really the diversity of all its accomplishments. So just those are a couple of accomplishments that were noted in 2023 when it had been about 10 years. So of course we've got some exoplanet candidates. We've got how many stars it observes per second, about 3,400.
Wow.
These 800,000 binary stars. We've got now all this information about it. 25 countries also that are involved in this mission, and the data yielded about 10,000 papers back in 2023. Many PhD theses as well, about 120. It's frightening to look at the amount of data that was gathered, 126 terabytes. So some really amazing accomplishments. And so we're going to end by looking at this wonderful image that they released in January 2025. You've all, of course, probably seen all these famous representations of the Milky Way. We can never have, of course, it's quite tragic. We can't have an image of our own galaxy because we can't send anything far enough away, fast enough to get out of the galaxy and get an image. That would be really nice. But now we've got this beautiful little image that shows this artist representation. We think that Gaia has contributed to the thought that we have more than 2 spiral arms. They're a little less prominent than we thought previously. And the central bar is actually more inclined with respect to the sun. So pretty amazing to get to refine this, especially again from inside. We're trying to map out our house from inside of it, right? And this is the edge-on view. So we've known since the late 1950s that the Milky Way, of course, is a disk, but it's not flat. It's actually a little bit curved, right? A little bit curved upwards on one side, downwards on the other. And so they used some data from Gaia. They were able to confirm that the warp is not static. It actually changes its orientation over time. This is precession, right? We see this with the sun, we see this with the moon, we see this with objects that are rotating. So just like, again, that little wobble that we have on a spinning top, so that warp is moving around the center of the Milky Way faster than we previously expected. It actually completes a rotation in about 600 to 700 million years. Still slower than the speed at which the stars in the disk orbit the galactic center. But we want to know now, is the Milky Way's warp caused by galactic collisions? Maybe with a Sagittarius dwarf galaxy. We think it's burst through the Milky Way several times in the past. Kind of, it's coming and going through the Milky Way. So we'll be able to have an even more precise understanding. And to answer your very good question earlier, Bill, is there a successor now that it's reached the end of its mission? So again, there's going to be a lot more data to come, but there is already tentative plans. There's not a lot of information on it, but there is a mission provisionally called Gaia Near, capital NIR, and this is a successor that will have near-infrared capabilities. So that would be launching in 2045. We actually want that delay in time, because we want to be able to then compare that data from 20 years ago to what we're going to get 20 years later with proper motions of stars and things like that. So they will be aiming to observe the same 2 billion stars, but it could actually increase this capacity with the near infrared to 8 billion stars, because again, we have a lot of stars that we can't see. They're behind dust. So it's going to be pretty remarkable. So I hope that this gave you a little insight on this mission that I think doesn't get enough press, and that really is doing pretty remarkable things, and that really, again, touches on all areas of astrophysics. So hopefully a lot more data to come. I think data 4 and 5 are going to be really exciting. So even though it's ran out of propellant and it is officially terminated, we will still have a lot of exciting news from the Gaia mission.
Thank you.
Crash positions, everyone.
Well, thank you, Laura May, for all that fascinating information on Gaia. It really has revolutionized much of what we know about the Milky Way. Just a fantastic mission that people didn't know about. Well, folks, that's a wrap for our online-only episode of All Space Considered. We really hope you've enjoyed it. I want to thank the panel. Thank you so much for making this possible, everybody. All Space Considered is brought to you by the City of Los Angeles Department of Recreation and Parks, Griffith Observatory, of course, and as always, we thank Griffith Observatory Foundation, our exclusive nonprofit partner. Thank you, everybody, and we'll see you next month at All Space Considered.